So our speaker today is Tyrone from the University of Maine. And his title, you see there, is Frobenius C-star algebras and local adjunctions of C-star correspondences. Please, Tyrone, go ahead.
All right, well, thank you very much for the invitation, and thank you all for coming. So what I'm going to talk about is some categorical ideas that are connected to C-star algebras and representations of C-star algebras. And this whole circle of ideas began with a concrete application in mind to representation theory, and I'll say a little bit about that at one point in the talk, but most of this talk is going to be somehow programmatic. What I would like to do is pose a question, motivate that question, and then provide some preliminary evidence that suggests that the question at least has a sensible answer, even if I don't yet know what that answer is. Right, so the question is a question of what are the morphisms? And to set up that question, I need to tell you first, what are the objects? So here is a picture that is, I guess, familiar to many of us in the world of non-commutative geometry, at least from the C-star algebra point of view. We imagine a dictionary where with spaces in one column and algebras on the other. And so for each locally compact Hausdorff space X, we consider the commutative C-star algebra C0 of X. And those are all the commutative C-star algebras. And then we just imagine that a non-commutative space is whatever fits into the dictionary next to non-commutative C-star algebras. Then the question arises, what about maps of spaces? So over in the spaces column, we have continuous maps between spaces. And the question is, what does that look like on the C-star algebra side? And now, as I guess many of us know, if the C-star algebras have a unit, then putting star homomorphisms of C-star algebras, just maps between C-star algebras that preserve all of the algebraic structure, that's a pretty reasonable thing to put in there. But if the C-star algebras don't have a unit, for example, if they look like this, C0 of X for a non-compact space X, then for many purposes, just that naive idea of star homomorphisms is not the right one. What is the right one? Well, here's one possibility. So to each C-star algebra, we can associate the so-called multiplier algebra, M of A, and this is defined as a certain space of maps from A to A, which we imagine as left multiplication by some element of this big algebra M of A. And the condition is that there should exist an adjoint, because we want the multiplier algebra to again be a C-star algebra. So it should have an adjoint satisfying this equality, which says that if you multiply on the left by T and then take the adjoint, that's the same as taking the adjoint and multiplying on the right by T star. Okay, in this way, we get a unital C-star algebra into which our A embeds in that way. And some familiar examples, if we started with the C-star algebra of compact operators, then we do this multiplier algebra construction, we get all the bounded operators on the same Hilbert space. And if we start with a C0 of X vanishing at infinity functions, what we end up with are bounded functions, or in other words, continuous functions on the stone-check compactification. All right, and this multiplier algebra then gives us one way to fill in this blank spot in our dictionary. A homomorphism or a morphism of C-star algebras, denoted by this dashed arrow here, is going to be a star homomorphism, not from A to B, but from A to the multiplier algebra of B, which we require to be non-degenerate in the sense that every element of B should admit a factorization, something in B times something in the image of this map. All right, if we do that, then at least in the commutative case, we get all of the continuous maps of locally compact Hausdorff space.
Sorry, you do not allow for sums here. So AB doesn't mean the linear span of products, but just the actual products.
It turns out to be the same thing in this case. For C-star algebras, there's a so-called factorization theorem, which says that the closed linear span of the products AB is actually equal to just AB. This is the Cohen-Hewitt factorization theorem. Okay, so this, for many purposes, this is a satisfactory way to go, but not for all purposes, because when we're doing non-commutative geometry with non-commutative C-star algebras, a lot of the time we want to identify, for example, the space of scalar valued functions on some space with the space of matrix valued functions on that same space. We should regard scalar valued functions and matrix valued functions on the same topological space as really being the same non-commutative space. And these morphisms don't really permit that identification. There's no isomorphism in that case. So what we would like to do is get some more morphisms so that these Morita equivalences, of which I just mentioned an example, and Morita equivalences of C-star algebras should be somehow isomorphisms of non-commutative spaces. There should be morphisms that realize Morita equivalences. So one way to do that, certainly not the only way, but the way that I'm going to discuss today is, instead of thinking about a non-commutative space as an algebra, we're going to do a familiar operation in geometry, and instead of looking at a space, we're going to look at a category of sheaves. I mean, this is just an analogy. What we're actually going to look at is, instead of looking at as a C-star algebra, we're going to look at a category of modules over that algebra. And the modules that I'm going to use are the Hilbert C-star modules. And then the question of what is a map of non-commutative spaces, the answer is going to be some kind of functor between these categories. And I'm about to explain what all of this means. So firstly, what is a Hilbert module, Hilbert C-star module? And I imagine that many of us here know this. So just a quick reminder. So if we have a C-star algebra A, then a Hilbert module over A is, to begin with, a module over A. And I'm always going to be talking about right modules in this talk. So it should be a module, and it should have an inner product taking values in the C-star algebra A that satisfies all of the usual axioms of a Hilbert space, except that in a Hilbert space you have the complex numbers here, and for a Hilbert A module we have the C-star algebra A. And so, for example, if A is a commutative C-star algebra and therefore looks like functions on some space, then what a Hilbert A module is a space of sections of a continuous field of Hilbert spaces over that base space. All right, and now what are the morphisms? We said we wanted a category here, so what are the morphisms between Hilbert modules? And here, again, there are different options that you might choose, each with its own advantages and disadvantages. Here are two options. One thing you might look at is the so-called adjointable morphisms. So if you have two Hilbert modules, X and Y, over the same C-star algebra A, an adjointable morphism between them is a linear map from X to Y that has an adjoint characterized by this usual equation characterizing the adjoint in the sense of Hilbert space operators, but now this is with respect to the A-valued inner product on A-valued inner products on X and on Y. So those are the adjointable operators. Now inside the adjointable operators, there's a subspace called the so-called compact operators. And what these are is, you take, to get an operator from X to Y, you fix an element of X and an element of Y. And what you do is you take inner product with that element of X to get an element of A, and then multiply by your chosen element of Y to get back into Y. You take all of the operators like that and take their closed linear span inside this space of adjointable operators, and you get what are called the compact operators. And so when A is just the complex numbers and we're just talking about Hilbert spaces, then the adjointable operators are precisely the bounded ones, and the compact operators are precisely what we usually mean when we talk about compact operators between Hilbert spaces. All right, and now we want to turn Hilbert modules into a category, so we need to choose what are the morphisms going to be. And I've just mentioned two of the possibilities. And as I said, each has its drawbacks. And so the adjointable morphisms, these are good things, and they're sensible things to understand. On the other hand, for some applications, for example, in K-theory, we don't only want to remember that there are adjointable morphisms. We somehow want to remember that inside the adjointable morphisms, there's this distinguished ideal in this category comprising the compact operators. Okay, another thing you might try to do is just use only the compact operators as the morphisms in your category, but then you immediately run into the problem that you don't get a category, because usually the identity operator, which you need in order to have a category, the identity operator is usually not compact. You see that already on Hilbert spaces, for example. Okay, and now one way that you can resolve this issue is to just resign yourself to working with non-unital categories. Just like at the beginning of C-star algebra theory, we resigned ourselves to working with non-unital algebras. So what we're going to do is consider this thing. For each C-star algebra A, we consider K sub A, which is a non-unital C-star category of Hilbert A modules. Those are the objects. And the morphisms are compact operators in the sense that I defined on the last slide. And now, if you don't know what a C-star category is, it's like a category. It's non-unital, so you drop the requirement that there should be identity morphisms. On the other hand, what does the C-star mean? It means that each set of morphisms is a linear space that has a star operation that switches the order of the spaces, and a norm, and making it into a Banach space. And the norm and the star are related by this usual C-star identity. And then you need to add in by hand this requirement that all morphisms of the form T star T should be positive elements of the C-star algebra of endomorphisms of the appropriate object. This business of what exactly is a C-star category is going to be in the background through the whole talk, but it's never going to really come to the forefront. So if you didn't swallow that definition all at once, then that's fine. All right, now one thing I will ask you to swallow, though, is the idea that working with non-unital categories is something that is, sensible and reasonable to do. And if you've been thinking about categories for a while, the idea of throwing away identity morphisms just seems like it would break everything that we do in category theory. But it turns out that maybe in general that might be true. Things would look very different, just like in algebra. When you talk about rings without identity and add no other requirements, then you end up with a bunch of crazy things like rings in which all the products are zero and things like this. But it turns out, just like in the world of C-star algebras, non-unital C-star algebras are actually not that far from unital C-star algebras. It turns out that non-unital C-star categories are not very far from ordinary categories, thanks to this construction of multiplier categories. So the study of non-unital C-star categories has been around for a while, and here are some of the names involved in this. The idea, just like with the C-star algebra, if you have a non-unital C-star category, then you can enlarge it to something called the multiplier category by doing the following thing. So you keep the same objects. So the multiplier category has the same objects as the category you started with. But what you do is add in extra morphisms. And the way you do that is you say, so a morphism in this multiplier category is a collection of maps. So for each object Z in the category, we have a map from morphisms in the original category from Z to X, going to the morphisms in the original category from Z to Y. And the way we think about this map is, it's what does it mean to compose with T? Just like in forming the multiplier algebra, we ask, what does it mean to multiply by T? Here we're talking about composing with T. And this map should satisfy some fairly obvious conditions. It should be compatible with the composition we already had in the category, for example. And there should be an adjoint, because we want this multiplier category to then be a C-star category. So this T should have an adjoint going the other way, and there should be some compatibility between composing on the left with T versus composing on the right with T star, and intertwining those two by applying star on either side. Okay, and this is really a generalization of the multiplier algebra construction, because you can view a non-unital C-star algebra as a non-unital C-star category with just one object, and the space of morphisms being the C-star algebra that you started with. And so if you do that, and you can apply this multiplier category construction to get a new C-star category with exactly one object and some more morphisms, and what you end up with is exactly the morphism space is now the multiplier algebra in the sense of the second slide, or whichever it was. Okay, and
yes, one thing, is there such a thing as an approximate unit for a non-unital C-star category?
I believe there are, for the reason that I believe it's true that every non-unital C-star category can be represented as a category of maps between Hilbert spaces. Just like every C-star algebra can be represented as bounded operators on a Hilbert space, every C-star category can be represented as a category in which the morphism spaces are bounded operators between Hilbert spaces. And then you get approximate units that way. So I believe it's true. Yeah, I think that's true. Oh yeah, it must be true because the endomorphisms of an object in a C-star category form a C-star algebra. And so each of those, so if you're going to talk about approximate units, they would have to live in the endomorphism algebras, and those are C-star algebras. So regardless of whether I've remembered this representation theorem correctly, I think it's true that you have approximate units as well. All right, and now going back to, where this whole non-unital stuff came up, at least in this talk, in trying to understand what should be the morphisms between C-star modules. And it turns out that by allowing non-unital C-star categories in the door, you really get, you somehow get the best of both worlds, because you look at the non-unital category of compact operators, but then you recover this bigger category of adjointable operators by taking the multiplier category, because the multiplier category of the compact operators are the adjointable operators. All right, and so I was in the midst of explaining this dictionary where we now think of non-commutative spaces as non-unital C-star categories of Hilbert C-star modules. And now I'm now going to explain this line. What's a map of spaces? I claim it's a good notion of a map of spaces should be something called a non-degenerate star functor. So what's that? So if you have two of these non-unital C-star categories, again, I'm going to use this dashed notation for one of these non-degenerate star functors. So what it is something that looks like a functor, not from C to D, but from C into the multiplier category of D, where by functor I mean something that sends objects to objects and morphisms to morphisms in this multiplier category that is compatible with composition. It should be a star functor, meaning that it intertwines the star operations on the two categories, and it should be non-degenerate in this sense here, that every morphism in D between two images of this functor should admit a factorization as some morphism in D composed with something in the image of this functor, some multiplier in the image of this functor. And so once again, if you look at C-star categories with just one object, which is the same thing as a non-unital C-star algebra, then what I've described is exactly this notion of morphisms, non-degenerate star homomorphisms into the multiplier algebra. Okay, and now what does this give us in the case of non-unital C-star categories of compact operators on Hilbert modules? Well, the theorem of Blecher implies that what we get are precisely these functors here of tensor products with C-star correspondences. So a C-star correspondence is a Hilbert module. It's a kind of bimodule. A C-star correspondence from A to B is a right Hilbert B module that is equipped with a left action of A coming from one of these morphisms from A into the compact operators on F. And this dashed line means that this morphism actually goes into the adjointable operators and is non-degenerate as a map into the adjointable operators. All right, and so many of us have worked with C-star correspondences before. They're the kinds of things that show up in KK theory, for example, and in other places as well. All right, so now we have this new dictionary where a space is the same thing as a non-unital category, and a map of spaces is one of these non-degenerate star functors. But now remember the reason that I proposed modifying this notion of morphisms to include Morita equivalences is that we wanted Morita equivalences to somehow come from isomorphisms. But now you maybe see the problem that it's not the case in general that if you have a Morita equivalence and you compose it with its inverse equivalence, you don't get the identity, you get something that's isomorphic to the identity. And so what we need, if we're doing this category theoretical point of view of this dictionary, is we need to know not just what are the morphisms, the maps of spaces, but what are the maps of maps? What are the two morphisms that would allow us to formulate what it means for two categories to be equivalent, and more general things as well. Okay, and now what should, how would we know we'd found the right thing to go in here? Well, we want to capture Morito equivalences between C-star algebras. So certainly Morito equivalences should be equivalences in this new 2 category that we're hoping to set up. And we don't want any more equivalences. We don't want all of a sudden spaces to get lumped together that ought not to be lumped together. And so we want the equivalences in this 2 category to be precisely the Morito equivalences. And then point 2, which is the one that I'll focus on for the rest of the talk, we want more than just Morito equivalences. We want a useful notion of adjunctions between non-degenerate star functors. And now there's a kind of obvious candidate for what is a morphism of non-degenerate star functors, at least in the case of between categories of compact operators. We said, this theorem of Blecher, that the functors we're looking at are just C-star correspondences. And now there's an obvious notion of a morphism of C-star correspondence. It's just an adjointable operator of C-star modules that intertwines the left action. So there's an obvious candidate for what goes in here. And that candidate does satisfy property 1. That's again still part of this theorem of Blecher, that taking morphisms of correspondences to be adjointable maps, that does have the property that the equivalences of categories of compact operators are now precisely the Morito equivalences. But I would argue that taking that notion of 2 morphisms leads to too few adjunctions. The notion of adjunction coming from putting adjointable operators here is just too restrictive. And I'll say on the next slide, I'll give you an example of something that I think should be an adjunction but isn't with that restrictive definition of 2 morphisms. And now I need to admit that unlike the red question marks earlier in the talk, the red question marks on this slide are not a rhetorical device. They are genuinely something I don't know. So what do I know? Well, for the rest of the talk, I'm going to suggest what kind of adjunctions we want to have. What should be an adjunction between 2 non-degenerate star functors? And then I'm going to suggest that that notion of adjunctions is the notion of adjunctions that comes in from some 2 category. There is something that we can put here that I don't know what it is yet. There is something that we can put here that would satisfy criteria 1 and 2. Okay, and the evidence is, it's not going to be the kind of evidence that would stand up in a court of law, but I think it's maybe an interesting, suggestive piece of evidence nonetheless. All right, so here's an example of something that is not an adjunction with respect to these the obvious candidate of 2 morphisms, but which I suggest should be. So it's a geometric example. Go ahead.
There is a comment in the chat.
Oh, I'm sorry, I'm not looking at the chat. Let's see. Yeah, it is very, very similar to that bicategory. It's essentially the same thing, except when you're talking about functors, it's not a bicategory because you have actual composition of functors rather than tensor products of correspondences. Oh. And so yeah, the bicategory mentioned in the chat, the bicategory of C-star algebras, C-star correspondences, and adjointable maps of correspondences is essentially the same thing as the 2 category that I am arguing against on this slide, the 2 category where the notion of adjunctions is, I claim, too restrictive. Does that address the question in the chat? Yeah, great. All right, so imagine taking an interval and folding it in half. For example, taking the interval from -1 to 1 and then taking the absolute value and folding it in half to give only the positive numbers. So that's a map of spaces, and associated to this map, we get maps of continuous fields of Hilbert spaces, or sorry, functors between categories of continuous fields of Hilbert spaces, or Hilbert C-star modules over the corresponding C-star algebras like this. There's a pullback and a push forward. And if there was any justice in the universe, pullback should be adjoint to push forward. But it turns out that they're not adjoint in the 2 category of C-star categories and non-degenerate star functors and adjointable bimodule maps, or in this bicategory of correspondences and adjointable maps that was brought up in the chat. the fact that we don't get an adjunction here is, I mean, it was not stated in exactly these terms, but it follows from a theorem of Kajiwara, Pinzari, and Watatani. And if I have time and if I remember to do this in a few slides, I'll come back and explain why this doesn't work here. But just to say the same thing in maybe a more explicit way, we don't have natural isomorphisms like this between spaces of adjointable operators from a pullback of x to y going to operators from x to the push forward of y. So this is another way of thinking about this adjunction.
Sorry, when you say for all Hilbert modules x and y, do you mean that there is a subcategory on which this actually is the case?
I imagine there would be, because I mean the only problem comes at the point that, I mean, at zero, at the hinge of this fold. And so if you somehow looked at a subcategory of modules that were, you know, supported away from that folding point, then it should work out fine. All right, so we don't have an adjunction like this, but nevertheless, I claim that, you know, if we're doing geometry with non-commutative spaces, something like push forward being adjunct to pullback should be a feature that we might want to have. And I claim that we can capture that feature using the following definition. So this is a definition coming from an old paper of mine with Pierre, Clare, and Nigel Higson. So a local adjunction between two of these star functors, or two of these C-star correspondences, is a natural isomorphism of the form that appeared down here. I mean, I guess that did not appear down here, and that was the point. But instead of looking at adjointable operators, we only look at compact operators. But a point of fine print, the natural. So we claim this with the definition requires a natural isomorphism here, and natural should be with respect to all adjointable maps. Okay, that's a minor point that need not bother us too much. Now notice that this definition, I've stated it only in terms of these categories of compact operators on Hilbert modules, but the same definition would carry over to any pair of non-unital C-star categories and pair of star functors between them. You just require natural isomorphisms of the morphism spaces, but natural with respect to all multipliers of those categories.
Sorry. So when you define your category, the one category, the homomorphisms were the compact ones, not all of them, right? Or not?
Correct. Yes, that's right. This KB means the objects are Hilbert B modules, and the morphisms are compact operators.
So this is the right definition of adjoint. Why should the L play a role if the category is just the compact?
Yeah. So this certainly does look like the right definition if you're thinking about you know, the definition of adjunction in terms of isomorphisms of Hom spaces. But as I'll get to on the next slide, if you think in terms of units and co-units, which is, you know, if you want to actually do something with an adjunction, a lot of the time what you want is a unit and a co-unit. And as we're going to see, that falls apart.
Since it's not unit, then
you don't have identity morphisms to map into the other space. Yeah. Yeah, so this certainly looks like it, you know, it should be what an adjunction is, but it lacks, at the moment, it lacks certain properties that make adjunctions nice to work with that I'll explain on the next slide. Okay, and so so what we did with Pierre and Nigel is we gave a description of when a pair of C-star correspondences admits a local adjunction like this, and the condition can be stated in a couple of ways. One way to state it is that there should be an isomorphism between F and G, which is a conjugate linear map. It should also be conjugate with respect to the A and B bimodule structures in this way. So F is an AB bimodule and G is a BA bimodule, and this isomorphism phi should act like a star in the sense that phi of AFB should be B star times phi of F times A star, and it should be completely bounded. So these a C-star correspondence is an example of an operator space. It can be embedded in a canonical way into a C-star algebra, into a space of bounded Hilbert space operators. And having done that, you get a canonical family of norms on the spaces of matrices over these C-star correspondences. And what completely bounded means is that when you extend this map to spaces of matrices, it remains bounded with a uniform bound on the norms. Okay, and then a third equivalent condition is something that appeared in this paper of Kajiwara, Pinzari, and Watatani, which they call the structure of a bi-Hilbertian bimodule of finite numerical index. And those of you who are familiar with this paper, it's important that we're talking about finite numerical index, not finite, if you like, algebraic index in the sense of Watatani. All right, one thing to notice about these local adjunctions is that they are always two-sided. You know, if you can put the F here and the G here, then you can just take stars and you get an adjunction going the other way. Or in terms of these maps phi, if you have an isomorphism from F to G, then the inverse will be an isomorphism with the same properties. All right, and so some examples. So this first line is just a reminder of what was on the last slide. So Morita equivalences are examples of local adjoints. This star map is just you take the usual adjoint of going to the inverse correspondence. These pullback and push forward functors from a couple slides ago, those are locally adjoint. You do get isomorphisms on spaces of compact operators, even if you do not get isomorphisms on spaces of all adjointable operators. And this is a special case of a general family of examples that conditional expectations that have finite index in the sense of Frank and Kirchberg, rather than in the sense of Watatani, again, for those who know this area, then you do get local adjunctions. And the example that motivates, sorry, question?
Yeah, so, I mean, you do not get, I mean, are you saying that in order for the functors associated to two bimodules or correspondences to be adjoint, they need to be isomorphic? Because the phi has an inverse, or
yeah, the correspondences do need to be conjugate linearly isomorphic, and they need moreover to be, there needs to be some analytic content to that isomorphism. It's not going to be an adjointable map because you're switching the bimodule, the order of the bimodules. You know, F has a B valued in a product, while G has an A valued in a product. So you can't really compare them as C-star modules, but you can compare their operator space structures, and we require the operator space structures to be the same, again, up to this conjugate linearity that involves taking a matrix transpose.
So the existence of such a map already implies that it is bijective.
Yes.
Any such map is bijective.
Yes, that's right. Okay, and here's the example that that motivated us, meaning me, Pierre, and Nigel, to look at this. It's really somehow building on this folding the interval example. If you imagine the interval as being somehow a space of irreducible representations of a group, like at least half of the irreducible representations of the multiplicative group of R, and then this folding map represents what happens when you induce those representations up to SL2R. You get some intertwiners that the representation of minus A is isomorphic to the representation sitting over A, and so you get this folding map. What happens in general if you have a real reductive group like SL2R, and you have a parabolic subgroup like the group of upper triangular matrices, then you do get one of these locally adjoint pairs of correspondences which correspond in the world of representation theory to operations on representations of parabolic induction, which is the one that I was just talking about, and this adjoint functor of parabolic restriction. So there you have a local adjunction, but not an actual adjunction in the sense of adjointable operators. Okay, and a nice property of local adjunctions is that if instead of looking at Hilbert C-star modules, you look at Hilbert space representations. So in this example, we're talking about unitary representations now of G and of L, the Levy part of this parabolic, then you get an actual adjunction on spaces of bounded operators, bounded Hilbert space operators. Okay, this is not going to be the focus of the rest of the talk, just to kind of explain why we started thinking about this. All right, now getting back to the question of, what's wrong with this notion of adjunctions? Why isn't this just obviously the right thing? Well, if we had an adjunction in the sense of bounded adjointable operators, then by taking suitable choices for x and y, and by plugging in an identity operator on one side, we would get a canonical operator on the other side. And to make a long story short, what we would end up with is a unit map, which would go from the C-star algebra A into this tensor product, F tensor G, and a co-unit map going from G tensor F to B. And now you could consider these as natural transformations of functors in a way that I won't go into. But having done that, what you end up with is another way of describing an adjunction that only has to do with maps between bimodules. It doesn't have to do with isomorphisms between Hom spaces. And this unit and co-unit picture of adjunctions is often the one that is most useful when you're actually doing algebra doing categorical algebra with adjunctions. So it's certainly something that we would like to have for local adjunctions. But as I said, the way you get these maps is by plugging in an identity on one side of this isomorphism, and back in the world of local adjunctions, you probably don't have identities all the time. And so it's questionable whether there are units and co-units for local adjunctions. And so you don't, so in this situation here that I have denigrated as being too restrictive, in this situation, the unit and the co-unit are actual adjointable maps of C-star correspondences. You definitely don't have that in this case of local adjunctions, but you have something that seems like it ought to fit in C-star algebra theory. And here's why. So for the unit, we're trying to get a map from A into F tensor G. Now, F tensor G, it turns out, is isomorphic as an operator space to the C-star algebra of compact operators on F. And now, so the question is, do we have a map from A to the compact operators? And the answer is, we kind of do. We have one of these morphisms coming from the action of A on F. So up to completely bounded isomorphism of operator spaces and up to taking multiplier algebras, which is what this dashed arrow means, we kind of do have a unit. And similarly, we kind of do have a co-unit by identifying this tensor product with compact operators on G, and then applying this formula, we end up with not a morphism of C-star algebras, but a completely positive map of C-star algebras like this. So again, up to completely bounded isomorphism of operator spaces, and up to allowing not just star homomorphisms of C-star algebras, but completely positive maps, we do have something that looks kind of like a co-unit. And so these kind of maps are the kind of things that we would want to include in our hypothetical two-category.
Well, one little question. Does it make sense to imagine or to talk about approximate units and co-units in this setting, as you have in many, C-star algebra?
Yeah, that's a good question.
Maybe this description is something that somehow can be approximated by actual things that do not live in a higher.
Yeah, that is an interesting suggestion. I'm not sure right now what to say about that, except that it's definitely something that would be worth thinking about. Yeah, so sorry, I don't have a great answer to that, but it's a great question. All right, and so so a conjecture, or it would be more accurate to call it a guess, really. My guess is that there is a two-category. There is an appropriate definition of what the two morphisms are. What should be the homomorphisms between C-star correspondences that satisfy these conditions, which were called 1 and 2 a little while ago, that the isomorphisms in this two-category, the equivalences of categories are exactly Morita equivalences of C-star algebras, and the adjunctions are local adjunctions, or I mean something that's a lot like local adjunctions, maybe a little bit more general or a little bit less general, but something like this. All right, and why do I conjecture this? Why do I think that that such a two category exists? So this is more recent work. The idea is that it's known that if you had an actual two category, then the two-sided adjunctions in that two category would correspond to some algebraic object called a Frobenius algebra. So if there were a two category, then local adjunctions would correspond to some kind of Frobenius algebras. And what I'm going to explain very quickly is that local adjunctions do correspond to some notion of Frobenius algebras, which is somehow, I think, a very natural C-star algebraic version of the classical notion of Frobenius algebras. Okay, so firstly, what's the standard definition of a Frobenius algebra? So on this slide, everything is just algebraic, no C-star algebras. So if you have a ring with unit, then one way to define what a Frobenius algebra over that ring is as follows. So you have a ring C and a homomorphism from A to C. And when I say homomorphism of rings, I mean unit preserving homomorphism of rings from A to C. And so that homomorphism makes C into an A bimodule. And so a third piece of structure here is a bimodule map going the other way from C down to A, having the property that if you take the tensor product of C with itself over A, which you can do since C is an A bimodule, thanks to eta, and you define a multiplication on this tensor product like this. You take two elementary tensors and you contract in the middle by using this map epsilon to squash them down to A, and then move it on one side of the tensor or the other, it doesn't matter. So that gives you an algebra, and the condition that characterizes Frobenius algebras is that this algebra should have a multiplicative identity. Okay, there are other characterizations of Frobenius algebras in terms of co-multiplications and other things, but this is the one that works best for my purposes. All right, and now what's the connection with adjunctions? So Morita proved that on the one hand, if you have a bimodule, just an ordinary bimodule now, between two rings, A and B, which has the property that the tensor product functor with F that takes an A module and spits out a B module, if that functor has a two-sided adjoint, then the endomorphisms over B of this bimodule F is a Frobenius algebra over A. So Morita proved that two-sided adjunctions lead to Frobenius algebras, and vice versa. Every Frobenius algebra arises from a two-sided adjunction like that. Okay, and now this is a statement about functors between categories of modules over rings, but it actually turns out to hold in much, much more generality. So this is really the end of a very long story, this theorem of Lauder, that every two-sided adjunction in any two category gives rise to a Frobenius algebra in an appropriate monoidal category, and vice versa. Every Frobenius algebra comes from a two-sided adjunction. So the two concepts are really one and the same thing. All right, how to turn this into something C-star algebraic. So above the line is the definition that was on the previous slide. And now here's how I modify it. So we want to work with C-star algebra. So now A should be a C-star algebra, not required to have an identity. And now so Frobenius C-star algebra over A is a C-star algebra C, again, not required to have an identity. And instead of talking about a unit preserving homomorphism of rings, we want to have one of these dashed homomorphisms of C-star algebras. So a non-degenerate star homomorphism from A into the multiplier algebra of C. And again, we want an A bimodule map going back the other way. And we require this map to be completely positive because we want to end up building positive definite inner products using this map epsilon. So this map, we need to assume positivity here should be completely positive. And there's a non-degeneracy condition, which I want to gloss over right now. You generally expect that when you're dealing with non-unital C-star algebras, trying to mimic something that works for unital C-star algebras, you need to include some kind of non-degeneracy, and here is what you need to do here. Okay, and now this condition, we build this tensor product again, but we don't just take an algebraic tensor product, we take the so-called Horup tensor product of C-star algebras. And so what this is you take the free product of these two C-star algebras C amalgamated over A via this map here. And inside that C-star algebra, you take the closed linear span of things that look like a product of something from the first copy of C times something from the second copy of C. So this is not a C star subalgebra of this free product. It's just a closed linear subspace of this C star algebra. Nevertheless, we can make this thing at least into a Banach algebra using the same formula as before, and this map epsilon. And the condition is that we call this thing a Frobenius C star algebra if this Banach algebra has a bounded approximate identity, meaning a bounded sequence that when you take that sequence and multiply it by any element of this algebra, then the result converges in norm to the thing you first thought of. All right, and now I claim that these Frobenius C star algebras correspond to local adjunctions in the same way as this theorem of Morita. So let me remind you, Morita's theorem said that bimodules that have a two-sided adjoint give rise to Frobenius algebras by taking endomorphisms, and every Frobenius algebra is the endomorphism algebra of a functor with a two-sided adjoint. And so the theorem that I have here is essentially the same thing in the world of C star correspondences. So if you have a C star correspondence with a local adjoint, in the sense of an isomorphism of compact operator spaces, then the endomorphisms of that algebra in the non-unital C star category sense, the compact operators, the C star algebra of compact operators on that correspondence is a Frobenius C star algebra over A. And moreover, every Frobenius C star algebra is the C star algebra of compact operators on some C star correspondence admitting a local adjoint. And moreover, there's a matching up of isomorphism classes. All right, and now just to very briefly, without delving into any of the details, to very briefly indicate how this works. So suppose we have a local adjunction. So let's try to prove part one. Suppose we have a local adjunction of C star correspondences. What that means, remember, is that we have a conjugate linear isomorphism between F and G. Okay, now we're trying to turn this C, this compact operators on F, into a Frobenius algebra over A. Okay, so to do that, we need, remember, we need a map from A to C, which we have because F is a C star correspondence, and so A acts on F, and so we do have an action map from A into the multipliers of the compact operators. So that's given to us by the bimodule structure. Okay, this map here, this epsilon going back the other way, this comes from identifying compact operators, this space of compact operators with F tensor G in the way that I indicated a little while ago when we were talking about units and co-units, and then doing something to turn using the A valued inner product that we have on G and getting a map like that from C to A. So that's where epsilon comes from. And now remember, the condition is that this Horup tensor product, this Banach algebra, should have a bounded approximate identity. Well, it turns out in this case, this Banach algebra is isomorphic as a Banach algebra to a C star algebra, namely the compact operators on this C star correspondence F tensor G. And being a C star algebra, of course, it does have a bounded approximate identity, like all C star algebras do. So this is how we get from local adjunctions to Frobenius C star algebras. How do we go the other way? So suppose we have a Frobenius C star algebra, so this data here, a C star algebra C, and a morphism of C star algebras from A to C, and a completely positive map from C back to A, satisfying this condition on a bounded approximate unit. So we want to obtain a pair of locally adjoint C star correspondences. So what we're going to do is, for our F, we're going to view C as an AC bimodule using the map eta on the one hand and just the obvious action of C on itself on the other, equipped with this standard inner product on that any C star algebra carries as a C star module over itself. So that's our F. And now our G, the adjoint thing, is again going to be C, now as a CA bimodule. We just multiply in the opposite direction. But now the inner product, the A valued inner product, comes from doing this standard C valued inner product, but then mapping down into A using this completely positive map, epsilon. And the fact that epsilon is completely positive ensures that we do get a positive definite inner product here. All right, and now what we need to get a local adjunction is to have an isomorphism between F and G. Well, F and G are the same space. They're both C as a space, we want a conjugate linear map from C to C, which somehow switches the order of multiplications. The AC bimodule structure becomes CA. So what we want to do is just use the star map on the C-star algebra C. And it turns out that that is what works. But to make sure that we do get a completely bounded isomorphism of operator spaces, we need to make sure that the operator space structure on C coming from this inner product here, using the epsilon, is isomorphic, is completely boundedly isomorphic to the standard operator space structure on the C-star algebra C. And the hard part of that is showing that the norm that you get, or the family of matrix norms that you get on C from this inner product are not shrinkingly small compared to the C-star algebra norms. Okay, and I've written out roughly how that goes. There's an algebraic part. This is where you use the existence of a bounded approximate identity. You want to compare norms in C to norms in C tensor C. And the way you do that is using this bounded approximate identity. Okay, and once you've done that, then a simple application of Cauchy-Schwarz gives you the estimate that you need. Okay, those details are just supposed to be an illustration of why a bounded approximate identity, what that has to do with comparing operator space structures on C. All right, and so in conclusion, the problem that I've been describing is to answer the question of, what are the morphisms? What are the right morphisms? And the objects that we're looking at are what are the right morphisms between C-star correspondences, or more generally, between non-degenerate star functors of non-unital C-star categories. And the answer to that question should have the properties listed here, that it should give rise to precisely Morito equivalences of C-star algebras, and moreover, local adjunctions, or something that is similar to local adjunctions. And as I said, the results in category theory culminating in this theorem of Lauda says that if such a thing existed, then local adjunctions would correspond to Frobenius algebras, and the theorem that I've just finished describing is that local adjunctions do correspond to something that looks like it deserves to be called a Frobenius algebra in the world of C-star algebras. So there's still a lot of loose threads to be tied together. And in particular, I still don't know exactly what kind of maps we want to take here. And yet, I think that there's hope that it can be made to work, and that we can arrive at somehow the right categorical structure, the right two category in which to study C-star algebras and their representations. So thank you very much for listening.
Thank you, Tyrone. Let me see if there are questions in the chat. Meanwhile, in a completely different context, namely in relation to bound-cone conjecture, people talk about non-unital C-star categories. So you have a functor or a certain category of spaces that associates to each space a certain non-unital C-star category, and then you want to do something like K homology, the invariant K homology. And then there is this construction of Michael Joachim that essentially is, you take a C-star algebra. A C-star algebra is a C-star category.
Yeah.
Okay. And now so this gives you a functor from C-star algebras, C-star categories, and this has an adjoint, which that's okay. And so to any C-star category, unital or not, you associate a C-star algebra. And then you can pretend you really have C-star algebras for your sections, because you simply define, say, the K-theory of the system category as the K-theory of this sister algebra, right? And this is functorial. So, do you think there might be any use for such a construction in this context?
I would guess that the answer is yes, because this, if this construction of going from a C-star category back to a C-star algebra somehow gives you the right thing in K-homology, well, K-homology and K-theory, being Morita invariants, they only depend on the category of C-star modules. So somehow, going from C-star categories to C-star algebras, if it has good K-theoretic properties, then it ought to somehow, it ought to capture the same thing that you're trying to capture when you look at the C-star category of Hilbert modules. I mean, this is a very, hand-wavy answer, but I would imagine that's something like this might be relevant. Is the way you get the C-star algebra? I'm sorry, I knew this at one point, but it's long ago. Is the way you get the C-star algebra is you represent the category as bounded operators and then take somehow the C-star algebra that's generated by all those operators, or?
I mean, I know. So let me tell you the non-C-star version of it. Right? So you take a linear category, meaning that you may add the homomorphisms, and then you take the direct sum of all the home groups.
Yeah.
Now take the tensor algebra on that, and divide by whenever you have two composable maps, the product is a composition.
Right. Yeah. Okay.
That gives you a functor that associates to each linear category a ring.
Yeah.
That's adjoint to the inclusion of rings in categories, and there is a sister version of that, and this is what Mikhail Joachim did. But this is some old thing. But I was reminded of this because last Friday in this global non-commutative geometry seminar, Uli Bunke gave a talk on course homotopy theory, whatever, and he used this construction in the context of assembly maps, sister algebra assembly maps for topological K-theory, such as bound cone and liquid coarse bound cone, etc. That was what I brought it.
Okay. Yeah, I would imagine, thinking about it a little more, I think, especially if you look not at all C-star modules, but at countably generated ones, every countably generated C-star module is a direct summand of just L2 sequences of elements of the algebra. It's the Kasparov absorption theorem. And so it seems like what you get back, it might actually not be too hard to show that if you start with the category of modules and then form a C-star algebra like this, you get something that's fairly close to the C-star algebra you first thought of, maybe, stabilization or something like this. So yeah, the short answer to your question is, I think, yes, that construction would be very relevant.
Okay, so does anyone else have a question after of this talk? Well, I don't see any raised hands. So if not, let me stop the recording now.